Muhammad did lots of questions. And I think some of the questions are from the internet. But as soon as you can do it, you understand it's fine, because I'm not against internet or AI. This means that there's only one white? Okay. Can you find 5 more whites? Well, yellow is okay, but these are too colorful. Sana is a student in this group. She's not here yet. She reminded me last time when I was just finishing, she hung on to here for a week, hung on another nearly 30 minutes. She said, I need to tell everybody why the topics I'm introducing are important. Let me just write this word down in another color. Importance. Of topics. Some people write a lot about motivation and so on in their paper, of course. What do you think about the importance of these topics? We can figure it out if it is important, but it could be not important to anybody, because importance is with respect to some people. Right? Because something important to me is probably not important to anybody. So the importance is relative to individuals. But her question is still valid. So now I'm going to say something about the importance of this in mathematics. Do you think conic sections in analytic geometry is important or not? One. Quadratic equation, let us say. In analytic geometry, we all did this. Of course, analytic geometry also contains concept of distances and straight lines, line segment and midpoint of a line segment, and then ratio division. So you have 2 points in, for example, in the Euclidean plane at AB, then we have a ratio which is AC over CB is equal to some lambda. We can actually do that using only the coordinate systems. Those are the things which are in analytic geometry, and conic section is extremely important, right? And what does it go into linear algebra? These go into linear algebra as quadratic forms. She is not here, but somebody will probably take a shot of this. Quadratic forms are extremely important in linear algebra and in mathematics and in physics, isn't it? Because all those physical spaces is determined by one of those, what the quadratic form is like. If there's last coefficient is 4 variables and then last coefficient is negative, then it is Minkowski space. Otherwise, it's Euclidean space and so on, right? So if you want to really drag this far into politics, quadratic forms are important in mathematics and in physics, in theory and cosmology as well. Now, what did we talk about last time? Last time we talked about ellipses, hyperbola, and parabola. They are, if they have an equation there, if they're in the Euclidean plane, then they are called conic sections. But we are now moving away from Euclidean spaces. We are moving into other good, nice metric spaces. So what you mean that these are going to be my topics, which I introduced last time, those questions. These are moving into other nice spaces. You have to really know what nice means, but this is also subjective. But at least I can say some spaces are nice. For example, Riemann spaces are definitely nice, right? It has a positive constant curvature, and hyperbolic spaces are nice. But even in Riemann spaces and hyperbolic spaces, we don't know conic sections. That's what I tried to say last time. So, instead of shouting slogans and doing politics. This is applied in industry and this is applied in this and that. Instead of facing reality, we just face mathematics. Inside mathematics, quadratic equations are important in analytic geometry and linear algebra, and it was nicely done there. Nowhere else was done. So we are trying to move in there. This is the relevance of the topic. Now, today is the last lecture before suspension. We are going to only resume on the 1st of December. And I have received some emails from at least 5 of you. I think only one of them is here. So at least 5 of you sending me solutions. So we will, I renumber the questions because at the end of the monograph, which I prepared for this mini course, there are 10 or 20, 15 questions. And now we have added lots. So this renumbering is going from 1 to something like 55 or something. So the original numbering is no longer, but in that order they will appear. The first one was this question here: determine the sets of rational points from the first lecture. Let me not write all of the questions so that we save some time. Rational points in one is space is given by x squared plus y squared is 2. In full writing, this is actually x equal to round bracket xy colon x squared plus y squared is 2. And bracket is closed. It's that set. And then the second one is 3. I don't need to put this now because it's actually quite natural. Third one is 4. Square is equal to 4. And people who have contacted me did it very well, but now I'm going to write it. I will write the answer in full, the answer I gave. Because, and then after it is all done, I will upload so far I have 8 of these pages. Did it only this morning, typed this morning actually. So I'm working quite nicely now. First of all, 1 is circle with radius root 2. Of course, root 2 is not a rational number, but after you square it, it looks like it's a rational something. On the right side it was a rational number and so on. You shouldn't be confused about that. So the 1, answer to the 1, we first of all, let us call this x equal to, in each case, x, y, it's all in the Euclidean plane. And this equation, and then close the bracket, and this equation goes back. In that x, first of all, we see that if you substitute 1 or negative 1 in x and y, the equation is satisfied. So altogether we have known by doing these 4 points. We'll write these 4 points. 1, 1, 1, negative 1, negative 1, 1, negative 1, negative 1. These 4 points are in the space. And we see that every coordinate is either 1 or negative 1. 1 or negative 1 are rational numbers. Yeah. So these are rational numbers on this. And then this gives us an idea. Of course, I should draw a picture, but I don't think you need it. Let us go choose any one of these points and make a straight line through it, which has a rational slope. So let us choose that one. So the equation of a straight line through, for example, 1, 1 with slope t. And the slope is the parameter. which is a rational number, is, you can write it down easily. Y equal to tx minus t plus 1. Y minus 1 is equal to t times x minus 1 plus 1. And which you can simplify as y equal to tx minus t plus 1. This is a nice linear equation with a straight line. And this point is on in the space X, on the circle, which is actually in the first quadrant. Now this straight line can be tangent to this circle at that point. Otherwise, it will intersect because this point is already on X, in X, it will intersect the circle in exactly one other point. And we're going to find it out. In order to find it out, we substitute this y into that equation. School mathematics. And then we simplify and we get an equation, a substitution. Then we write down only the key words completely. The substitution into original equation produces a quadratic equation of x. 1 plus t squared, x squared, minus 2t times t minus 1, x. So the first degree coefficient is negative 2t t minus 1. And then the constant term is t squared minus 2t minus 1. This is in terms of the x coordinate. We now regard it as an unknown, and then t is the parameter, rational parameter t is now a constant. And then, of course, many people who gave the answers use the root formula. You need to use that. The root formula is, in my opinion, is never used when I do questions. It only makes sense with respect to Galois theory, so that quadratic equation definitely can be solved using arithmetic operations and good thinking. But otherwise, we always do otherwise, but we can easily factorize if it can be, even if it is not integers, we can easily factorize by cross multiplying. Now we don't even use that. We know that x equal to 1 is one of the roots. Even if you can substitute x equal to 1, you will have 0 on the left hand side. Because the line goes through that. So this 1 is a root.
Yes, sir.
So x1 equal to 1 is a root. Is the solution. People who like word solution instead of root. How about the other root? Other root, we're going to find it from here. The other root, let us say, is x2. But x1 times x2 is equal to negative c over a. By via thus theorem.
Yes.
Now we just know this is your c here. This is your a there. So x2 is equal to x1 is 1, so if it goes to the denominator, it didn't do anything. Divided by 1. So x2 is equal to negative c over a. C over a, yes. C is t squared minus 2t minus 1. A is equal to 1 plus t squared. This is x2. Now let us find y1. y1 is there, so we're going to find. So y1 is equal to that. And y2, just substitute in here. y2. Or x2. Or y2. y2 you can also find by substituting this back into that one. That is too much trouble. I will leave it here. And after finding it, you have that this is a rational function of t, that is a rational function of t. And when t is a rational number, then rational function of a rational number is also rational numbers. So these two are both, the main thing is they are both in Q. we don't need to even write it out, but we can actually substitute this x2 in here. This time that is rational, that is t is 70 plus 1. If you add it up, it's rational function of t. That's all we need. Rational function of t, therefore these two are both, the two coordinates are both in, actually for every rational number t, the pairs of solutions are all not rational numbers. So this gives us the complete answer to this. Now, after doing this, you need to really recover those 4 points as well. The first one is no problem. You don't need to require. You just have to say here what x is 1. So t minus t is 0 and y is 1, and where you can get this one. X equal to 1 equal to 1 implies x equal to 1 implies y equal to 1. When you are doing this kind of very elementary mathematics, you should not really look down upon it. Lots of great ideas are inside hidden. You can exploit. What about that point? X is 1. Y? This gives 2 ones actually. How to get negative 1 from this? To get negative 1 from this, t cannot be 0. If t is 0, this is 0, that is 0. Behind it, negative 1. With this negative, you get positive. So when t is 0, you get the first option, first point. How to get t equal? How to get y equal to negative 1? The expression of y. Let us now copy it. Expression of y is negative t squared minus 2t plus 1, t squared plus 1. How to get negative 1 from this? It's easy, isn't it? Let t go to infinity, positive infinity. And then you factor t and then cancel, then you have negative 1 here, negative, 1 there. That one is 0. Its limit of that over t squared is 0, limit of that over t squared is 0. So this, when t goes to infinity, the limit of y2 is negative 1. So y2 comes out like that. So we recovered that point. Similarly, you can recover this one. Now it's easier because that one is x is negative 1. X is negative 1 means that in this one you go, t goes to infinity. In this one. In that one, t also goes to infinity, you get 1. Negative 1. How do you get y equal to 1? Anyway, I did actually find all of this in this one. These are all obtained now. That one can also be obtained easily. What is happening is that that's even easier because now if you substitute, in this one you tell that t equal to infinity. In this one you just substitute also t. That is 1 negative 1 negative 1. So you can figure it out. All these 4 points which were known before are in the parametric expression. Can each be given by the parametric expression. This is one observation. The other observation is those people who submitted, I think it was Naira, didn't find any other point. You should really give 1 point which is other than those 4, using those formulas. It can be easily done just by substituting certain t in it. Then you will find 1 point which is other than this, t is 4. That can be asked because are these points all of them? No, t can take countably infinitely many values, and it is potentially those two expressions will give you countably infinitely many rational points in the space. There's a nice question in here, and that probably, I don't know if it is known or not. If a circle in the Euclidean plane has 1 rational point on it, is it possible that that will have only finitely many rational points on it? This is one question. This can be asked anytime from you, probably not in the exam, but I'd like to ask again and again when you're really interested in this. Another thing is if the contraposition, which is the word I don't like, if the rational points in this space, such space is finite, then can we say that it must be empty set? This you should really try. This is only for Euclidean plane, but what happens when you suppose that you have the Riemann sphere in centered at the origin radius 1, and you're going to intersect with any plane. Any plane means that this plane may not be parallel to any one of the coordinate planes. It could be something skew. And then it can actually be just tangent, and then it can be any circle intersection. It could be one of the circles will be a great circle. What happens to those circles in RC? The two questions I have asked, will they still have the same answer if you have managed to do the Euclidean plane? Any suggestion? Any feeling? You need to feel for mathematics, not just think. I always want my students to really put your hands on it, not only just lots of school teachers there. Use your brain. Yes, use your brain, but you should really first of all use your hands. My slogan is this. You should try feeling. Suppose that we are intersecting a sphere in 3 space by a plane, by any plane. Then the intersection is empty, 1 point or circle. If it is circle, then among continuum many circles in any direction, only one of them is a great circle. Only one of them goes through in each direction, the normal of this plane, in each direction there's only one which is a great circle. Yes, and what happens to, is it possible that if one of these circles, any one of these circles has a finitely many, has a rational point on it, then it has to be infinitely many. First question. Second question is equivalent to it is that if you assume that the rational point set is finite, then it must be empty. And we're going to see one which this is empty. This one has no rational points. Yes. Quite surprising. So how did we prove this? Of course, internet has lots of incorrect and correct proofs. The proof has a quotation mark around it when I say it. Please. You need to know that there were lots of nice results in the 18th century until 19th century by the famous people. Two famous people, one of their name is Fermat. Famous Fermat, who was not a mathematician. Or he was a mathematician, but all his life, he never stood in any lecture or attended no conferences. He was a lawyer all his life. And also independently by Euler himself proved that something called sum of two squares theorem. Any integer, of course, being sum of two squares, it has to be positive integer, non-negative integer. Any integer which can be written as sum of two sum of squares of two integers, some integer a, b, if and only if that n has to satisfy certain condition. The condition is that the square free divisor of that is not 3 mod 4. For any n, let us say it is natural number, but 0 is trivial. There exists a, b, which are integers, such that n is equal to a squared plus b squared. If and only if the given is serial solution condition, the square free divisor can contain a square unit. For example, 12. 12 contains 2 squared. 2 squared times 3. So the square free divisor is 6 or 3. So you cannot just check 3. N is not congruent to 3 more than 4. You just have to divide the square free factor of n by 4 and then see if it is remainder is 3 or not. If remainder is 3, there is no solution, no integer solution. If the remainder is not 3, then there is a solution. For example, if the remainder is 2, then it has, this can be expressed as integers, sum of 2 integers. And there are 4 ways in this case. So through using this, we have this one has no x has no rational sign. You are not interrupting. There is a question here. You should really try to make me stuck. Fermat-Euler theorem says about what? About integers, and we're talking about rational points. If there, I have a hidden thing behind me which says that if there's no integer solution, then there's no rational solution. Is that easy to prove? If it is not easy to prove, then I'm hiding something which is vital. You need to consider it. It's not difficult to see it. What if we are only considering, for example, slope that this has a rational solution? Let us say we make the common denominator. A over B, C over B. So it will give you A squared over B squared, C squared over B squared. And if we multiply B squared on the other side, that only becomes the square, non-square free part. It becomes the square part. 3 still is the square free part. So, and then left hand side is integer sums. Right hand side is also integer. So if that has a integer solution, then the original rational solution exists. Otherwise, it's if and only. So this you should really know. This is elementary number theory. So things I am hidden behind my back is not something which is really. And then we just use this space to do the third. Divide both sides by 4, then you have x over 2 plus y over 2 squared is 1. And we know that any number r is a rational number if and only if half r is also a rational number. Is this true?
Yes.
Therefore, this reduces to the unit circle case. And unit circle case we didn't do, but we did display infinitely many solutions. So this completes the first question, and I will erase and go to the second question. Anybody want to take a photograph of this board? Come and take. Of course, I'm going to upload it after everything is done, but which means not very soon. So after taking the photograph, I will erase the board because we now have only one board available. Yeah, and then you upload into the group if you want. We only take one question so far. Don't rush because we need to really have this all digested.